Giovanni Russo from the University of Catania. We will speak about semi-implicit IMEX schemes for evolutionary PDEs.
So first of all, I'd like to thank the organizers, Giacomo Marco and Lorenzo Bareschi, for giving me the opportunity to come back to Ferrara, which is a place that I like very much, and not only for the food. Is it the title of the talk? It's about semi-implicit IMEX schemes for a variety of evolutionary nonlinear partial differential equations. And this is the outline of the talk. After a brief introduction, I will describe the general semi-implicit approach. And I will show here there are some kind of academic simple examples just to see how this approach works. And then there are two major applications which are not trivial. One is the case of degenerate convection diffusion systems, and the other one is about how to construct schemes for all Mach number flow. And then I draw some conclusions. So there are several physical systems that are described by, let's say, stiff and non-stiff terms. The prototype case is the case of a hyperbolic system with a stiff relaxation. As epsilon goes to 0, formally the variable v becomes equal to f, and when you substitute it here, you obtain that the system, 2x2 system reduces to just a one single scale elevation for u. And this is a formal procedure that can be justified if a suitable subcharacteristic condition is satisfied. And this can also be generalized to higher order systems. So in general, these systems can be have two different parts. An explicit one part which is non-stiff, one part which is stiff. Now, in many cases, for example, the non-stiff, if you have a stiff problem, then you would like to use an implicit scheme to avoid stability problems. On the other hand, in many cases, the part which is non-stiff is perhaps complicated to fit implicitly. There is actually no need to fit it implicitly. So the idea is that you treat the non-stiff part by an explicit scheme and the stiff part by an implicit scheme. And that's because perhaps Laurent that the vibration disappear on the image. In this case, we say that the stiffness is additive, so the right-hand side is a non-stiff term plus stiff term. Another case is a case in which the system is partitioned, which means that you may imagine that the system is associated rather than to the function, is associated to the unknown itself. So, for example, in this case, we have a system of two equations, u prime is equal to f for qp, epsilon p prime is equal to g of qp. In this case, we call this case a partition case in which the stiffness is associated to the variable. U is a non-stiff variable and V is the stiff variable. Now, the two cases are actually they are actually very much related. For example, if you consider variable y just the variable uv, and then you consider function little f, the function capital F0, and the little g, 0 and capital G, then you realize that a partitioned system can be seen as a particular case of the additive system. It is also possible to do it is true the other way around. The converse is true. If you set and in this case here, y is equal to u plus v, then equation 1, you have u prime plus v prime is equal to f, some function f of uv, plus 1 over epsilon g of uv. And then you can give some freedom in this splitting of the unknown, and you can choose the splitting in such a way that you go with this position here, you can go back to expression number 2, which means that at the price of doubling the number of unknowns, a system which is in an additive form can be cast into a partitional form. From a practical point of view, this may be not so nice to double the number of unknowns, but from the theoretical point of view, the fact that these two systems can be cast in the same form is very useful, because once you derive, let's say, once you do the analysis for one system, automatically the results of the analysis for one of these systems is automatically can be applied to the other system. Now, a natural choice for all these cases will be implicit-explicit schemes. Now we will consider a more general class of system and see that even if the stiffness does not appear in an additive or in a partitional form, it is still possible to use more or less standard IMEX schemes that you find in the literature, and for free you get that the order conditions that otherwise would be very complicated to derive, order conditions will be automatically satisfied once you choose an IMEX scheme that already satisfies the order condition. And the observation is the following: if you consider now a more general equation for u, in which you have that the dependence on the unknown is this function h, you can say that the unknowns appear in several contexts, and the dependence may be non-stiff in some cases and stiff in some other case. Now this form here is not additive nor partitioning, but you can play some trick and you can recast this form of equation in the previous case. For example, if you just copy this, you say if you want to emphasize the stiffness, you can set y is equal to 0 over epsilon, and then this system here can be written as y prime is equal to h of t y z over epsilon, and epsilon z prime is equal to h of t y z over epsilon. So now in this form, this is my fault, I touched the cable. That's my fault. Perhaps I touched it. It's very sensitive. So, but if we really double the system, we will see whether
you should stand a little bit far away.
Far away, and electromagnetic. I don't know. So, do we really need to double the system, which is not very nice because the cost increases? Well, consider now this system here. And now, since this system is written in the partition form, we can apply an IMEX scheme. An IMEX scheme is obtained by two Buchet. Something strange. Perhaps the project is very tight.
Yeah, I think
very tight. I will try to be very fast. There's a couple Buchet tableau, and you can compute the function evaluation for the explicit part and for the implicit part using this tableau here. This is the explicit part with the matrix A. This matrix A hat is a lower triangular matrix with 0 element on the diagonal, and typically this matrix A is a lower triangular matrix with non-zero value along the diagonal. So once you do this, you can compute the evolution equation y plus 1 and z n plus 1. Now, it turns out that if the C coefficients are the same, you can show that the value of k and n are the same, so there is no need to double the number of unknowns. But also in other cases, if the b value are the same, also in this case these two are the same. But even if the b value are different, then what happens is the following. In principle, you have two set of variables, two set of evolution, yn plus 1 and zn plus 1. On the other hand,
Mattia went to search another projector. So
another projector?
Yeah, Mattia went to search for another projector.
Oh, you went to search for another projector, so we will see. Okay. So what I want to say is that if these two are different, then in principle these two quantities are different. On the other hand, if these two discretization correspond to a numerical scheme which is of order p in time, then these two quantities will agree up to order p with the exact solution. So you can choose, you can use either one. And if they are different, actually it is even better to choose values of b. What do you suggest, Lorenzo? If you use b which are different, what happens is that you actually, this is a good idea to use different values of b. You will obtain two different numerical solutions at a new time step, and in fact you can use the difference as a tool to check, to construct automatic time step control. In any case, in all these cases, there is no need to duplicate the variable. This is only a way to show that if you use an IMEX scheme for this more general problem, then you can get a high order scheme in time with no additional effort. Now we show some application. The first case is the reaction diffusion problem, which you have a set of two unknowns, two equations with two unknowns, omega 1 and omega 2. There is some Laplacian here, and there is some nonlinearity here. What we do is that we don't have a general rule, but roughly speaking, you should try to identify what is the stiff part and what is the non-stiff part. Well, here, for example, it is not difficult to imagine that the diffusion term is stiff. Perhaps we can make implicit one of this omega 1 square, we can write as the product omega 1 times omega 1. So here, this is the same as before, but in red we call V the stiff dependence, in blue U the non-stiff dependence. So this is the system, and we treat the red parts implicitly and the blue parts explicitly. And what we said before, automatically we guarantee that the accuracy in time is equal to the prescribed to the expected accuracy, order of accuracy of the IMEX scheme. In fact, if we apply, these are SSP2, so these are strongly stability preserving schemes of order respectively 2 and 3. In fact, there is no surprise that the numerical order of accuracy is in agreement with the theoretical prediction. This is a nonlinear conventional diffusion equation, and here we treated the nonlinear part explicitly, and we only put treat implicitly this term here, the V term here, and the V term here, where there is a Laplacian. This is linear but it's stiff because there is a Laplacian. And even in this case, there is no surprise, the order of accuracy is equal to the expected one, second order and the third order for the respectively SSP2 and SSP3 schemes. This is another case in which you see that the equation is nonlinear, but really the stiffness is not due to the nonlinearity. The stiffness is due to the fact that this equation is a fourth order equation in space and first order in time. So you would expect that an explicit scheme would have a restriction if t less than some constants times 2dx to the fourth. It's very restrictive. So what do you do? Well, there is no need to treat everything implicit, so you can leave this quantity here explicit and only this part can be treated implicitly. This is, we performed a comparison with two solutions. One is an exact solution, which is this solution with compact support, which is this one. And then, this is how we did it. Then there is another solution, I think it's written later. So this is what we do. We treat this part implicitly and this part explicitly. And of course, if you want to emphasize the fourth order accuracy, then we need to use also fourth order accurate scheme in space. We solve this problem with the classical standard hyperbolic CFA condition. So the x dt is proportional to the x. And this is what we obtain is that in the two test case, one is obtained with the exact solution, but the solution, because it's a compact support, it is not smooth. There is a discontinuity in the derivative at the beginning of the support. So the order of accuracy is not exactly 2, but is like 1.6. But the other test case is the case in which we added a source term and we constructed an exact solution by adding a source term on the right hand side, and we constructed a smooth exact solution of a modified Kirchhoff problem. In this case, there are no surprise, the second order scheme and also the accuracy of the second order scheme is second order as expected. Now, these are we move to the other two test cases. These are more challenging test problems. The first one is comes from a joint work with Sebastiano Moscarino, Raymond Baker, Pet Moulet, and Luis Miguel Vilada. And we consider two cases of convection diffusion systems in which the right-hand side is a diffusion term which may be degenerate. This matrix V can be singular. So there are two applications of a system with this structure. One application is a model of Pauli dispersed sedimentation, and the other one is a multi-class lightly Richards traffic flow model. I will not go into details about the model. I would like to go directly. First of all, so I will concentrate on the numerics. First of all, we discretize the system by kind of a method of lines approach. The flux term is treated explicitly, and this is the diffusive term, which is the one that is treated implicitly. Now you see that the diffusive term is the stiff part, and it is non-linear. But you can write as a matrix that depends on the unknown times the unknown itself. I skip the details about the model, and I will go to the numerics. Two kinds of schemes are considered. I remind you that the stiff term is the diffusive term. And now you have two choices. One choice is to use, so in any case you treat the convective part by an explicit scheme, and then about the diffusive part you have two choices. One choice is to use a fully implicit scheme to solve the diffusive part. And this, of course, requires some Newton iteration to find phi n plus 1. The other possibility is that you can treat this in a semi-linear way, which means you treat the argument of this matrix P in an explicit form, and this term here, you can treat it implicitly. In this case, we call the first one is IMEX, and the second one is semi-implicit IMEX scheme. So semi-implicit explicit scheme, S-IMEX. Now, these are the results obtained on a typical test case with 4 species. These species are basically small particles, and the different size. In this case, we assume we have 4 families of particles with different size, and phi is proportional to the concentration of each of these set of particles. And if you look at the particle with sediment, and this is the position. If you look at the picture, this is the superposition of numerical solutions obtained by the 2 schemes. They overlap. You have to enlarge some part of the picture to see some difference, and then you will see that there is some difference in the solution. Now, roughly speaking, what we observe is the following, that the scheme that when we use the fully implicit treatment of the diffusive term, of course they're much more expensive because they're fully nonlinear, but they give a better results. These are the results obtained by this fully implicit, and these are the results obtained by the linearly implicit. The linearly implicit is less accurate near the discontinuity. Now, let's do some more quantitative experiment. We can compare the accuracy and costs, similarly to what Tito showed. If you compare the accuracy versus just the number of grid points, then you will see that the fully nonlinear schemes, these dashed line are the semi-linear, and these are the nonlinear. The nonlinear give a better result. But if you compare the error not as a function of the number of grid points, but as a function of the CPU time, then the converse is true. In other words, in this case, these are lots of schemes that we compare, and we see that the winners are these schemes here that are all linearly implicit. So linearly implicit is a little bit less accurate for the same number of grid points, but is a little bit more accurate for the same number of the same computational time. So the same is for the other model, the one that takes into account the modified Lytle-Wheeler-Richards model of traffic flow. The behavior is similar. If you go to error versus CPU, then these are the. Unfortunately, I changed the notation. Now the semi-linear are in continuous, and the non-linear are dashed. Sorry for changing the notation. But in any case, the message is the same. Namely, the IMEX is sharper and less oscillatory, but requires a rectangular solution, therefore is a little bit more expensive. The semi-implicit explicit approach gives a slightly degraded solution, but there is no iterative solving, so it's more cost effective. Now, it could be interesting to explore the possibility of using the hybrid scheme. That's something we have in mind, but it's some work in progress with no results so far about this. Then the last topic is the topic of Hallmark numbers. Today we heard a talk about this problem. And probably I can go very fast about when the Mach number is very small. Well, this is the typical CFL restriction that you have in hyperbolic problem. It has to be less than dx divided by the maximum speed, and classical for species schemes. In classical Euler equation, the the maximum speed is just the velocity of the gas plus the sound speed. For incompressible flow, of course, we don't have acoustic wave. The acoustic wave basically at an even speed they carry no energy, and then if you write the incompressible Navier-Stokes equation, the incompressible Euler equation in this form, where this is the divergence free projection of the term u dot grad u, then if you use explicit in code, because this requires resolution of some elliptic problem to apply this divergence free projection. In any case, if you use some explicit solver, then of course the stability restriction that you expect is to have dt less than dx divided by the maximum velocity of the fluid. So there's no sound is involved. So you would like to obtain a numerical scheme that smoothly will converge to a numerical scheme for incompressible Euler, even when the sound speed goes to 0, or if you want, when the Mach number goes to 0. The reason why you can do that is that, well, if you have a high Mach number, the flow is compressible, and so you have shock discontinuities. The CFL condition is physiological because you are in general interested in acoustic waves. In the small Mach number case, the flow is almost incompressible. Very often you are not interested in resolving acoustic waves, and in fact, the shocks do not form if the emission data is smooth and the acoustic waves are negligible amplitude. So in this case, to be forced to satisfy classical CFL condition is a pathological case, because this restriction is only due to the stiffness and nothing to do with the accuracy you want to reach, so it should be avoided. This talk is about semi-implicit. In some cases, and this is something I said, we do not have a general rule to predict when a semi-implicit approach is better than a fully implicit. In fact, we will present, roughly speaking, the same two cases that we are presented today. 1D small Mach number isentropic Euler equation and full Euler system. And we will see a result which perhaps could be a little bit surprising. We start with the isentropic gas dynamics. M is equal to rho u is the momentum density. We denote epsilon the Mach number. So we have epsilon squared. This morning we can use the epsilon to be the square of the Mach number, so there was an epsilon. Our epsilon squared is equal to the epsilon this morning. And the system is closed by the relation P is equal a constant, which we set to 1 times rho to the gamma. Now, in order to avoid any difficulty related to the numerical flux, we use a staggered grid, which is very similar to have a staggered version of the Rosanov flux, more or less. And I think it's very similar to Giacomo. It's very similar. So you write the density at the new time step is equal to all density, and then you want to treat the momentum term implicitly. And then you write the equation for the momentum at the new time step. So the old one, then there is some part which is basically rho u squared that you want to treat explicitly, and then there is this new term. Now the new term contains 1 over epsilon squared. So you don't want to treat this term explicitly, otherwise you have a restriction on the time step. So how do you do that? Well, we try two things. We try to compute this PD to be the new density, the density time n plus 1 to power gamma. Or the other possibility is, well, we say Perhaps we can do some linearly implicit. This is almost like a Laplacian. It's a Laplacian in the pressure, but rather than a Laplacian in the pressure, we can say, okay, we linearize this. We say that rho to the gamma is equal to rho times m to the gamma minus 1 times the rho at the new times n plus 1. In this case, we would have a sort of a linearized equation for this sort of this is a nonlinear Poisson equation. Well, the result is the following. If you do that, well, in practice, it's much easier to use the pressure as a known rather than the density. So this is the Laplacian, the nonlinearity is only the diagonal, so it's much easier to apply Newton's iteration. Well, the result is that we did a classical test that we took from the paper of the Gonentan, and the result is the following. If you use this semi-implicit explicit in the way I linearized, the method does not work. There are oscillations that propagate, and this oscillation will never go away. So this approach does not work. You have to use the nonlinear elliptic solver for the pressure. If you do that, in fact, this is for epsilon equal 0.8, and this is for 0.3, and then there should be another. This is for 0.05. So we repeated basically the results of the Von and Tan. These results are, I don't know if you see the picture. This is very, okay. The dotted line, which is this here, is the result of the implicit scheme. Of course, the goal here is not to have accuracy. You cannot have accuracy because you have acoustic waves, and the method is not designed to capture the acoustic waves. It's designed to be robust and to filter you want to filter the acoustic waves. So, if you solve this nonlinear elliptic equation for the pressure, you are able more or less to reproduce the same result of the Gonentan. And then we switch to the complete Euler equations. In this case, you can play the same, more or less the same game. You use a staggered rate, the density a new time step, momentum a new time step, energy a new time step. But now the energy, there is a term here, and this term you emphasize this is E times U. First of all, E plus E, it appears only just a gamma factor. This is E, this is basically E plus P. And then you have U. U write as a M at the new time step divided by the density. And now here we try to play again the semi-implicit, which means we try to use to have only the momentum at the new time, and we leave the energy and the density at the old time. What you do is that you write a similar equation for the momentum at time n plus 1, but not centered in cell j plus 1/2, but centered in cell j. Then you take the difference between these two terms and plug it here, and then this is what you obtain. I mean, you take mj and plug it here. You write the equation for mj plus 1 and plug it here. And then what you obtain now is a linearized, I made a mistake. There is this is not U, sorry, I made a mistake. This is E divided by rho. These coefficients should be E divided by rho. In any case, the message is that you obtain the new energy is equal to something that you can compute explicitly, plus a three-diagonal part, which is the three-diagonal matrix times the energy itself. So it's now a linear system that you have to solve. So the system now, the approach now is linearly implicit. And In this case, we consider again classical test problem to a colliding acoustic pulse, and in this case we obtain the same results from the literature, from the complete Euler equation. So the message is that in some case this semi-implicit approach works, in other cases it does not work. This result are first order. We have a second order scheme, but these are still first order results, and we have a second order scheme. We didn't present in the second order because the second order is a little bit more involved, and I would say I can go directly to the conclusion. IMEX, coupled with the finite difference of finite volume, provide an effective tool for the numerical solution of a vast class of systems containing stiff and non-stiff terms. And of course, one has to identify the stiff and non-stiff dependence. We don't have a general rule for this, but a little bit of experience and intuition may help understanding what is the stiff part. In many cases, this is where you have the real advantage. The stiffness is linear, and this approach automatically gives takes care of the not of the stability problems, but of the accuracy problems. And then, of course, there's a very simple semi-implicit scheme has been obtained for Euler equation. It would be very interesting to generalize to other cases. And it is not, this is work in progress. There is still a lot to understand in terms of stability, and a general framework is under investigation for the construction of high-order Olmach number on stable grids. It would be interesting also to extend this to other cases, which is also a work in progress. And thank you very much for your attention.
Questions or comments?
Could you please go back to the slide where you showed the Olmach number for full Euler system?
Yeah, there was a mistake.
Energy.
The last, that's a mistake. There was a mistake in the last one. The energy equation.
But the unknown is the pressure or the total energy?
Oh, that's a good question.
Because here, as far, exactly. Is it true that you take the total energy as an unknown here?
Yes, it's the total energy.
Okay.
And
but
the total energy is very close to the pressure. When the Mach number is 0, is almost.
But have you tried to take the pressure again as an unknown? Because this would also allow you to have basically the nonlinearity on the diagonal, right? Because
yes, it's almost the same. It's almost the same. It's almost the same because as Mach number goes to 0, exactly. Pressure and density they're almost the same.
But not if you are. Yeah, in the limit, in the low Mach number limit. But if you want to run this at all Mach numbers, then of course far away for high Mach number flows.
For like 1.
Yeah, or even supersonic.
Ah.
Have you tried this? The alternative option, it would be the same as if what you have discussed before, right? That you have the choice whether you take density or pressure as primary unknown.
Right.
And you could do the same here as well, right? Take pressure as unknown and put the nonlinearity on the diagonal.
Right, no, I get that.
Okay. And sorry, can I ask the same question? The splitting, as far as I understand here, is basically the same as Tito proposed, right? So in the energy equation, actually what you split into the explicit part is just the convection of kinetic energy, right?
Right.
Exactly, so it's exactly the same split, which is, by the way, the only thing which really works in this as semi-implicit framework.
That's right.
Yeah, I tried the Tsar Bilgen and all this stuff, and the only thing that really works is this one.
Same.
Yeah, it's the one that you use and the one that Tito uses.
Wow. Yes.
One question: you are using rho to the n in the last equation, in the internal energy equation, in total energy equation, in the last term.
Yeah. Yes.
Divide by rho times n.
Yes.
You try to divide by rho times n to this one because you have access to it. Is it true or not?
No, I don't have access.
You don't have access?
No, because the first thing I do once I substitute this here,
Okay.
I would like to have, if it works, of course, I would like to have a semi-implicit. So it's a linearly implicit. I solve for the energy. Once I know the energy, I plug it here and I compute the momentum. And once I know the momentum, I plug it here. So the density is the last thing.